Welcome back to Reinforced Concrete Design. In this lecture, we will be looking at the design of flanged reinforced concrete sections. To understand flanged sections, let's look at what that looks like in real life. We'll look at the Wellgate Shopping Centre, which is located in Dundee, Scotland. Here you can see the Wellgate's reinforced concrete floor, which consists of a continuous slab monolithically cast with beams. A cross-section of such a floor would look something like this. As you can see, the beam will interact with part of the slab, creating a flanged section. The flanged section can be L-shaped or T-shaped, depending on where the considered beam is located. The same design procedures are applied in both cases. Due to monolithic casting, the slab works together with the beam. In zones of sagging bending, the slab increases the area of concrete in compression. In hogging, it will look something like this, so we can see that the area that is in compression is not increased. First, let's consider where the position of the neutral axis can be. It can either be in the slab, or it can be in the beam under the slab. The presence of the slab in the beam cross-section introduces two possible design situations. The first design situation, on the top right in the slide, shows the neutral axis in the slab. In this case, the slab provides all the compression. Since concrete intention is ignored in the model, it is not important how much concrete intention is present in the section. Therefore, such a section is designed as a rectangular with the width equal to the effective width of the slab. In the second design situation, the neutral axis is in the beam below the slab. This can occur when the slab is thin, or the spacing between the beams is small, and the applied bending moment is large. In this situation, the slab is assumed as fully stressed and the beam provides the remainder of the moment. Let's now try to answer what part of the slab should be considered as the flange. Initially, it can be assumed that the flange should extend over two half spacings between the beams from both sides. To understand whether this assumption is acceptable, we need to consider the theory used in the analysis of beams. The behaviour of beams is modelled using simple beam theory, and that states that a plane section before bending remains plane after bending. In the real structure, shear strains cause the plane section to warp after bending, as you can see here. The warping of the initially plane section indicates that the beam stresses developing in the concrete flange are not uniform. This contradicts simple beam theory of bending. As a result, the bending stresses are higher near the beam and lower at points remote from it. You can see this distribution in blue on the right-hand side. This effect is described as shear lag. The question is, how do we take it into account in our design? Shear lag is dealt with by reducing the width of the flange from half the beam spacings on both sides to what we call an effective width. The following assumptions are introduced in the model used for the design of flanged sections. The width of the concrete flange is reduced to an effective width. The bending stresses in the concrete flange are assumed as uniformly distributed. And the area of uniform bending stresses is kept about the same as the area of the non-uniform bending stresses. Let's consider how the flange section works in a continuous beam. In the sagging bending zones, the flanged beam has a T-section, because the flange is in compression. In the hogging bending zones, the flanged beam has in effect a rectangular section, because the flange is in tension and is ignored in the model. According to Eurocode 2, the effective width is calculated based on distance between points of contraflexure or points of zero moment in a beam. For example, the distance between points of zero moment in a simply supported beam equals to the beam span. In continuous beams, however, the distance between these points is found from the bending moment diagram. The effective width of the flanged beam is calculated for both hogging and sagging zones. The effective flange width depends on several factors, including type of loading, support conditions, beam span and spacing, web and flange dimensions, and transverse reinforcement. Eurocode 2 defines the distance between points of zero moment for different spans in a continuous beam in figure 5.2, shown here. The effective flange width is found using the following formula. Here, BW is the width of the beam, and B effective I, or B EFFI are the clear flanges on both sides of the beam. BFI is found depending on beam spacing and the distance between points of zero moment. The design of the flange section starts with a calculation of the parameter K. The depth of the neutral axis is then found and compared to the depth of the flange to check if the neutral axis is in or under the flange. The design procedures then depend on the position of the neutral axis. If the neutral axis is in the flange section is designed as a rectangular section with a flange width. The design proceeds with the calculation of lever arm and then of the area of bottom steel. Then the number and diameter of bars are selected and the spacing between bars is spread over the web width and calculated. When the neutral axis is under the flange, the design can be carried out in two methods. The first method is based on the calculation of the depth of the neutral axis. The second method is more conservative and is based on setting the depth of the neutral axis to its limit of 0.45d. The first method will be used in this module. When the neutral axis is under the flange, the area of compressed concrete is complex. Therefore, two design models are possible to use depending on how the area is divided. In the first design model, the complex area of compressed concrete is divided between the entire flange and the web under the flange, as shown in this slide. The force produced by the compressed concrete is also divided into the force in the flange, FCF, and the force in the web under the flange, FCW. The values of the compression forces are found using the rectangular stress block method, which defines the distribution of the compressive stresses in concrete. As you can see, the presence of two compression forces requires the evaluation of two lever arms, Z1 and Z2. The design starts with the evaluation of the moment MF carried by the flange. Since the force FCF is positioned in the middle of the flange, the lever arm Z1 equals D minus HF divided by 2. The moment generated by FCF can be calculated by taking the moment around the position of the tension steel. The total moment generated by the section can be found by adding the contribution of the compression force in the web, FCW, times Z2, to the moment MF produced by the compression force in the flange. To find the contribution of the web to the moment, the depth of the neutral axis in the web should be known. Since the rectangular stress block method is used, only 80% of the depth of the compressed concrete is assumed to be stressed. Therefore, the depth of the neutral axis in the web is also reduced. The depth of the neutral axis in the web under the flange can then be found for the expression for moment, which gives the following quadratic equation. Once the depth of the neutral axis in the web under the flange is found, the position of the neutral axis can be calculated from the geometric relationships. The area of bottom tension steel is calculated from the equilibrium of forces, where the tension force in steel balances the compression forces in the flange and the web. Finally, the number and diameter of bars is selected, and the spacing between the bars, which is spread over the web width, is calculated. In the second design model, the complex area of compressed concrete is divided between the clear flanges and rectangular beam as shown on this slide. The force produced by the compressed concrete is also divided into the force in the clear flanges, FC1, and in the beam, FC2. The values of the compression forces are found using the rectangular stress block method, which defines the distribution of compressive stress in concrete. As you can see, the presence of two compression forces requires the evaluation of two lever arms, Z1 and Z2. The design starts with the evaluation of the moment MF carried by the flanges. Since the force FC1 is positioned in the middle of the flange, the lever arm Z1 equals to D minus half of HF. The moment generated by FC1 can be calculated by taking the moment around the position of the tension steel. The total moment generated by the section can be found by adding the contribution of the compression force in the beam, FC2 times Z2, to the moment MF produced by the flanges. Basically, the design proceeds further as the design of a rectangular cross-section that carries the moment M minus MF. Since the rectangular stress block method is used, only 80% of the depth of the compressed concrete is assumed to be stressed. The depth of the neutral axis can be found from the expression for the moment, which gives the following quadratic equation. The area of bottom tension steel is calculated from the equilibrium of forces, where the tension force in steel balances the compression force in the flanges in the beam. And finally, once again, the number of bars and the diameter of the bars are selected, and the spacing between bars is spread over the web and calculated. The top compression bars are required when the depth of the neutral axis is larger than 0.45 times the effective depth of the section. In this case, the concrete compression area is divided according to the design model 2 we discussed earlier. The top steel adds an additional compression force, FSC, to the force system. The value of this force will depend on the area AS tag and the depth D tag of the top steel in the section. Since the depth of the neutral axis is known, both compression forces FC1 and FC2 and their respective lever arms Z1 and Z2 can be calculated. The maximum resistance moment of the singly reinforced flange section is found by adding the contributions of the flanges in the beam. The expression for limiting the moment can be made dimensionless by dividing by FCK times B times D squared. When M, the moment, is bigger than the limiting moment M limit, compression reinforcement is required. Compression reinforcement is found for the additional moment M moment minus M limit, the limiting moment. The area of the bottom tension steel is found from the equilibrium of forces, which gives the following expression. If the top steel is located too low, that is, D tag over X is bigger than 0.38, or D tag over D is bigger than 0.171, it does not yield. In this case, the compression force in the top steel is found from the linear distribution of strain in the section. And you can go back to see the doubly reinforced concrete section that we discussed in topic 3 for more details. In hogging bending, the compression zone in the flanged beam is in the bottom of the web. Since concrete in tension is ignored in Eurocode 2, the flange section is designed in hogging bending as a rectangular section with the width of the web. The continuous slab in the reinforced concrete floor is supported by the beam. Therefore, the slab is in hogging bending at the slab beam connection. Eurocode 2 requires the positioning of the tension reinforcement of the slab above the tension reinforcement of the beam. This should be accounted for in the evaluation of the effective depth of the beam section. The slab beam connection requires an additional check for longitudinal shear due to the shear lag effect. The tension reinforcement can be distributed over the effective width of the web. Part of the bars can be concentrated over the web width. We have now covered the design of the 3 different types of reinforced concrete sections: singly reinforced, doubly reinforced, and flanged. From now on, we'll have a look at deflections, shear, and then discuss slabs and columns. So join me next time when we delve into deflections.